Okay, so you can probably just jet through a few of those first pages. They're just trying to help you to develop the concept, but we can kind of short circuit or shortcut a little bit of those. There's a concept that Avogadro came up with, and that's that equal volumes of different gases at standard temperature and pressure contain the same number of particles. So basically, if I have a balloon full of hydrogen gas, then I have the same number of particles of hydrogen gas in that balloon as I would have oxygen gas in a similar balloon. So there was a bunch of, this is like 2, 3, and 4, the questions that were basically talking about that concept, saying that if there's a certain volume and they're at standard temperature and pressure, which is just basically room temperature at sea level, so just like everything's kind of the same, then there's going to be the same amount, particle-wise, of gases in any given space. So pretty much those little gas particles bouncing around, they sort of stay the same distance from each other, so you end up with a comparable amount in that same space. So that's one of the concepts that we kind of come back to a little bit later, and it turns out that the number for this is that, well, it's 1 mole of any gas takes up 22.4 liters of space. What's a mole? I'm glad you asked. Now a mole, when we were talking about that last little bit where we compared everything to hydrogen, when they started working with this stuff, carbon turns out to be a really useful thing to work with because carbon's really stable, it's always the same, it's not a gas. So they were able to use 12 grams of carbon as sort of their the stabilizing point. So hydrogen's a little harder to deal with. They started out with trying to deal with that, and then they went, okay, but hydrogen's comparable to carbon. If carbon's mass unit, like we were talking about before, were 12, and they did that with other experiments, then how much, well, we can compare the number of particles in 12 grams of carbon to any other element. So what they came up with was, okay, we're going to use this concept of a mole, and that's just the number of particles in 12 grams of carbon. So what we're saying is there's some number, and originally it was too hard to get that number, but they said there's a specific number of atoms in 12 grams of carbon. And it's going to be the same as this concept, where if I use that unit measure, then there should be that same number of particles for the unit measure of any other atom. So for example, if hydrogen has the unit measure of 1, then 1 gram of hydrogen should contain 1 mole of hydrogen particles. If I'm looking at the list, oxygen's mass, according to the periodic table, is 16. So 16 grams of carbon should contain 1 mole of particles. And later on, it was discovered that this is true, and that the number of particles in a mole is 6.02 times 10 to the 23rd. So that's why I posted that goofy song that basically talks about that concept and how big of a number that actually is. So it's a gigantic number. One of your other ones says it's hexillion. Yeah, this is, we're in the hexillion department here. So that was new for me. Those videos are really fun, but they're also really informative. So have a look at those if you haven't already. That explains the concept of what a mole is. When we established what a mole was, it turns out that 1 mole of a gas at standard temperature and pressure is 22.4 liters. So using this concept that equal volumes of different gases, as long as they're at STP, contain the same number of particles, 1 mole of those particles, so if you weighed a mole of hydrogen, it would be 1 gram of hydrogen, is going to take up 22.4 liters. So we can use these little connectors to convert from one thing to another. And that's what the main concept of this chapter is about, is converting between grams and moles and liters and numbers of particles.